So today's test is chi-squared for homogeneity. So like yesterday, what we did is we analyzed one variable in one population. So the number of each color of M&Ms, the grade distribution. So it was one variable, one population. Homogeneity test, you're looking at one variable in two or more populations. Again, the variable could have two or more categories. So this is like, everything we've done so far has been numerical. Now we're looking at categories. So here we're looking at one variable in two or more populations. So like, if you have a Salem students prefer a particular subject, that would be goodness of fit. If you wanted to know whether gender played a role, girls and boys, and which subjects they prefer, that's a test for homogeneity. Okay? So we're not going to just have a list 1, list 2. We're going to do some matrices today. So if we wanted to see different classes have different preferences, we would do homogeneity of proportions test. So here's what stays the same. The chi-squared test statistics stays the same. But the data comes from a two-way table instead of a one-way table. So expected values change, degrees of freedom changes. But the actual like expected and observed over observed thing, that stays the same. So if we look at this table, this is independent random samples were taken from voters from 4 different regions of the country, and that each voter's political affiliation was noted. Are political party affiliations the same throughout the U.S.? So when you're looking for homogeneity, you're just looking for the same. Is the proportion of Republicans the same in the Northeast, East, the South, the Midwest, the West? Are the number of Democrats the same? So you're looking for sameness. This is an example of a two-way frequency table. The number in the tables, these are your observed cell counts. Okay, so those are going to be your observed. In a test for homogeneity, remember, that's a big word. Homogeneity just means sameness. Okay, we want to determine if the category proportions are the same for all the populations. So you're just looking for sameness. In this example, are the proportions of political affiliations the same throughout the country? Now, notice we have Republican, Democrat, and we have other. Why do you think we have an other category? Not everybody falls into one or the other, right? But think of the amount of numbers. Think about yesterday's condition 2. Your expected cell counts have to be bigger than what? 5. So like if I were to separate all the non-Republican Democrat parties, like Libertarian, Green Party, the Tea Party, those numbers might get super small. So what we do to like cheat the system is we just create an other category. So if the sample, your sample size needs to be large. Our expected cell counts should be greater than or equal to 5. If we don't think that will happen, we combine categories. And create an other category. Okay, so it's kind of the way we cheat. So if you have, here we have 2 major political parties, and then everybody else just gets roped into that other category. Okay, so if you want to find the expected values, there is a mathematical way to do it. There is a formula, but we're going to use our calculator. If you flip to the back page, the next page, Since Republicans make up 0.429 of the overall population, according to the null hypothesis, Republicans should make up 0.429 of each region. So, like, our null hypothesis here would be that P1 equals 0.429. Since Democrats make up 44.2% of all the overall population, the null hypothesis is that Democrats should make up 44.2% of each region. So if I'm looking at proportion 2, that's kind of what we're asking. Okay, we're looking for sameness. So our expected cell count. You don't need to know how to do this, but you do need to know that it's a formula. So what they do is they look at the row marginal total and you multiply by the column marginal total, and then you total, and then you divide by the grand total. So there's a reason on a lot of these two ways tables they have the total, because all they're doing is they're taking like 472 times 272 divided by this. And then they're taking 137 times, to get this one, they would take 137 times 267 divided by this. We will use the calculator to find each expected value. Okay, so we're going to use some matrices today. So for a chi-squared homogeneity test, here's what your write-up looks like. Your first condition is, again, random samples, but now we're looking at more populations than just one, so you want independent random samples. So your observed cell counts are from independent random samples. Like in the political party example, each region was independent of the next region. Again, they're not necessarily going to say independent in the question. You have to kind of infer it. Condition 2 is still the same as yesterday. Expected cell counts should be greater than or equal to 5. Therefore, your chi-square distribution may be appropriate. The test we're doing today, and I promise I won't be too harsh on you in terms of your spelling, is chi-squared test for homogeneity. And it's really easy to see the difference between what we did yesterday and what we did today, because yesterday you had a list 1 and a list 2. Today you should have more than just a one-way table. And then condition 4, this one's a little bit different. You're going to have P subscript RC. And that stands for the proportion of each row column. So again, you want to try to make it as general as possible. This time you don't need a key. So like, you just want to write the true category proportion in context. So the true proportion of each political party in each region. True proportion of each political party in each region. So just give it like an overall view. Okay, what are we actually looking at? It's just to help figure out, are you really looking at the problem in context? Okay, so just like yesterday with the ho and the ha, this time, again, we're looking for the same. So your null hypothesis is, you don't have to like list them all, because you might not know the actual percentage. So your null hypothesis is just that the true category proportions are the same for all populations. So you want to use that word, same. The null hypothesis is just like yesterday. The ho is not true. The true category proportions are not the same for all populations. Again, it's a little tricky. We don't exactly know which one might not be the same. Like, you might not know that the Republican's not the same for each region. You can't specify. You just either say they are the same or they're not. So you still have to make a table really of just your expected cell counts. They want to see a table of expected cell counts because the observed is already going to be in a table on the paper. So they just need to see expected. Your test statistics, just like yesterday. Degrees of freedom is different. So degrees of freedom yesterday was just the number of categories minus 1. Today, it's the number of rows minus 1 times the number of columns minus 1. So if it's a 2 by 2, then our degrees of freedom are just 1. In this example, it would be 3 by 2. So we would have degrees of freedom of 6 here. Because there's 4. Don't use the totals. It's 4 by 3. So then do 3 by 2. 4 minus 1. 3 minus 1. So it's 3 times 2. That's how I get 6. Okay. And then just like we've been doing, once we get our p-value and our test statistic, we reject or fail to reject, just like we've been doing. Okay. You ready for an example? We only got one today. So, in a study of cancer treatments, patients were randomly selected and placed into one of two groups. The first group received, I'm not even going to try and say those words, CP, while the other group received BCNU. The responses to the treatments were graded on a quantitative scale and summarized in the following table. So either they got a complete response with the new treatment, partial, no change, or showed some sort of progression. And then your totals. Is there a difference between the two treatments? So when you see the word difference, it's kind of the opposite of saying we're looking for sameness. So that's how you know it's homogeneity. Plus, yesterday we would have only be looking at one population, so we wouldn't be looking at them split into two. So for our conditions, the first one, the observed cell counts are from a random sample, because they were randomly selected. Again, if they're also randomly put into two groups, you're okay. Now, for condition 2, you're not going to get your expected values till later in the problem. But I would just assume that they're all greater than 5. And if not, go back and erase the word, or add the word not, and proceed with caution. So all expected cell counts are greater than or equal to 5, therefore chi-squared distribution may be appropriate.
For condition 1, don't you just put independent?
Oh, darn it. Yeah. Thank you. Okay. Because this is the only one you have to do independent. Because tomorrow we're going to test for independence. So you don't have to do it. So chi-squared test for homogeneity. So P sub RC. So we got to be as like kind of general as we can in terms of what are the two things that we're looking at. We're looking at response to the treatment versus which treatment they get. So the true proportion of each response for each medication. So for your testing, it's weird, your ho and your ha are going to be like sentences. And that's going to show up again tomorrow. So your null hypothesis is that they are the same. The true category proportions for each response is the same for each medication. And honestly, when you write your alternate, you can just write that the ho is not true. Okay, so now you got to do your table. So here are my expected cell counts. Now, you don't have to do totals. So we have BP and CP. You have a complete response, partial response, no change, progression. So, how do you figure those out? Everybody got the calculators handy. The first thing you have to do, just like we did yesterday, is you have to put your observed values in. So we're going to use matrices. So you want to go to matrix A and go over to edit. So you got to go to matrix A and you want to edit matrix A. Second, x to the negative 1 power. Right under math. Make sure you go to edit. So this is now I always get this screwed up. 4 by 2 matrices. Nope, 2 by 4. So you put your observed numbers in matrix A. Oops, I did 35. So you put your observed in matrix A. You do not have to do the totals. Just each response with the 2 medications. Now you're actually going to go through and do the test. So when you go back to stat, go over to test. You want to go all the way down to test C, the chi-squared test. Just a regular chi-square test. And these directions are on the back. So you're going to go to the chi-square test. See, it'll say observed is now in matrix A. It's going to put the expected cell counts in matrix B for you. So then you can either hit calculate or you can hit draw. So here's your chi-squared, there's your p-value, there's your degrees of freedom. So what I tend to do is, like, I know I got to show the formula. So down here I'll write my sentence. A chi-squared of 4.599 gives us a p-value of 0.02 or 2035 with 3 degrees of freedom. So I'll write that out. And now I'll go back and put in my expected values. So to get to matrix B, there's 2 ways to do this. You can go to the matrix and just look for B. But the hard part is, like, you got to scroll over. Right? And sometimes it's hard to read. So how I do it when I do this is I go to matrix, I go to edit matrix B, and then I can see the numbers more clearly. So I go to matrix, go over to B, and I go to the edit part. So these are your expected values. It's okay, they're all going to be decimals. And then you just have to double check that your condition true 2 was actually true. So you got to make sure that they're all greater than 5. Bless you. So there's your matrix B. So again, you can just go to matrix B and hit enter if you want, but then it's, like I said, it's hard to scroll over. So I go to matrix and I go to edit matrix B, and then it's easy for me to get to the numbers like that are over here. Okay, now just like yesterday, I don't expect you to do all 8 things in your formula, but I got to see that you understand the formula. So I'm okay if you just do the first one and the last one. So 26 minus 28.813 squared over, and then you can just put plus dot 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 and then do the last one. 34 minus 36. And then you can always write chi-squared equals 4.599. If you want to put I mean, I wrote it in my sentence, but yes.
Why'd you use 36 and not 37?
Yeah?
Yeah.
This is that one.
Oh, so does it just...
Oh, I did this one. And I did this one.
Yeah.
I don't care which 2 you do, I guess.
Is that technically your last 2, though? Or is that your last one?
Yeah, if you go, I go this way.
Alright.
You want to go.
Well, okay.
As long as it matches, like, this one.
Okay.
Okay, question so far. So, let's look. Is our p-value greater than our alpha? Yes. So we're going to fail to reject. So it looks like we're sticking with the null hypothesis. So for our conclusion, since our p-value is greater than our alpha, we have evidence to fail to reject the claim that the true category proportions of each response is the same for both treatments. The question was, is there a difference in the responses? If there was a difference, we would be rejecting. So let's answer the question. It appears there is not a difference in the responses for the two treatments. Okay. Now, if we rejected, we would say it looks like there is a difference. Again, we can't say where the difference is. We couldn't say like the number of people with no change is greater than this one. We just know they're either the same or they're not. Okay. Questions on that one?